Hello students, and welcome to the video on octal and hexadecimal numbers. So why use octal hexadecimal numbers? So computers, microprocessors often use octal, hexadecimal and different codes to enable or simplify certain operations. And they also use display and easily read long binary numbers, as in this binary number. It's quite hard to immediately see its value. And even in decimal, it's a pretty big number, but in hexa, it's a pretty nice, small, compact number. And it's also relatively easy to convert from binary to hexadecimal and from hexadecimal to binary. So that's why binary gets used more than octal and even decimal in computer systems. But first, let's start with octal. Octal, so why octal? Octal means it is a numbering system with a basis of 8. Where decimal has a basis of 10, octal has a basis of 8. So this means the octal numbering system only consists of digits between 0, 1, 2, 3, 4, 5, 6, 7. And if you go above 7, you start at 10, 11, 12, 13, 14, 15, 16, 17, and then again 20, 21. So we don't have the numbers 8 or 9 in the system. So counting octal is similar to counting in decimal, except that the digits 8 and 9 are not used. And distinguish octal numbers from decimal numbers or hexadecimal numbers, we use a subscript 8, as what we have done in previous systems of 15. 8 in octal is equivalent to 13 in decimal. I'll show you a table later on. So octal to decimal conversion, since octal numbers base of 8, each successive digit position is an increasing power of 8. Like we have in binary, where it's a basis of 2. Here we have a power of 8. The evaluation of an octal number in terms of its decimal equivalent is accompanied by multiplying each digit by its weight and summing the products, as we have done for binary previously. Illustrated here, let's have the number 2374 in octal. So 2377, that is a mistake. Let me just fix that. So that is 7. Sorry for that. That's my mistake. So once again, 2374. So, and now we write, as we did with binary, we write the powers of 8 instead of 2, because it's 8 bases. So 2 times 8 to the power 3 is 1024. 3 times the power of 8 times 8 to the power 2 is 92, 56, and 4. And then that gives this number. It's the decimal value 1276. Now, converting decimal to octal, a method of converting a decimal number to an octal number is repeated by division of 8. Remember, in binary we had division by 2, bases of 2, so now we have 8 bases of 8. So just showing how this works. Now, in binary we didn't really needed to worry about the carry bit, because it was base of 2 and quite simple and straightforward. But here we have a remainder of 0.5, and that you have to multiply by your basis number to get the remainder. Okay, so we start with 1276 divided by 8, which is 159.5. So the 159 moves here, and the 0.5 we multiply 8 to get the 4. So this then, the first bit we work out is our LSB, or our least significant bit. So in our next step, we take 159, divide that by 8. The answer is then 19, and we have 0.875. So 19 goes down, and we multiply 0.875 times 8. That is equal to 7, and that's the second number. We then have 19 divided by 8, which is then 2.375. 2 goes down here, and 0.375 is equals times 8 is equals to 3, so that's why 3 there. And then 2 divided by 8 is 0.25. And when we see the 0, we stop, because 0 divided by 8 is 0, so it won't go on in any case. But then 0.25 times 8 is 2. And this last number, when we get to 0, is our most significant bit. And then writing down the number is 2374, which is the same as we've got previously. So just remember, the last one is the most significant bit, and the first one you work out is the least significant bit. Now moving on to hexadecimal. So like octal, Hexadecimal allows binary numbers to be presented in a more convenient manner. However, the hexadecimal digit can present 4 binary bits since it has 16 possible combinations. So here we have a table of decimal 1 to 15, so 16 numbers. The hexadecimal equivalent of those numbers. You see, once we get to 10, we start using letters A, B, C, D, E, and F. So F is equal to decimal 15, E 14, D 13, C 12, B 11, and A 10. And this is the octal equivalent, just to represent the numbers and show you what I mean. And here we have a binary equivalent. So see, a maximum number of 4 binary numbers can represent the hexadecimal number of 15. So that's why they kind of mix nicely. The maximum hexadecimal numbers can represent a maximum of 4 binary numbers. You'll see what I mean when you take an example. So converting a decimal to hexadecimal process is completed by repeating division by 16. Because we have a base of 16 numbers. So let's take 287 in decimal, in hexadecimal. 287 divided by 16 is 17. 17 goes there, and then we take the remainder, which is 0.9375 times 16. We get 15, or F. Remember, 15 is decimal, and F is in hexadecimal. So 17 goes down here. 17 divided by 16 equals 1.0625. So the 1 goes down here, and then 0.625 times 16 is equal to 1. So 1 goes there. And then 1 divided by 16 is 0. We have 0, so we stop. We can't go on. 0.625, and then we take 0.625 times 16, and that is equals to 1, which is our most significant bit. So 287 is equals to 11F. So exactly what we've been doing for binary, octal, and now hexadecimal. The first number we get is the least significant bit, and the last one is the most significant bit. So now converting hexadecimal to decimal. So we have a 2F4 in hexadecimal. Now if you see a letter in a number, it's hexadecimal. So 2F4 is hexadecimal. So we write down the power of 16 because we have a base of 16. So here we have 2 times 256, which is there. 16 squared is 256. Then 15 times 16 plus 4 times 1. And the answer is 756 and decimal. Now converting binary to hexadecimal, this is what we really care about. Since each hexadecimal digit represents 4 bits of binary when converting from binary to hexadecimal, the binary number needs to be broken up into groups of 4. Remember I said that a hexadecimal number can represent a binary, 4 binary digits. So 4 binary digits we call a nibble. So you have a nibble of 4 and then a byte of 8 and a bit which is 1. So to do this we start at the LSB and count 4 bits to the left until all the bits have been grouped. If the last group has fewer than 4 bits we add zeros to the end as this does not change a binary number. So here we have this very long binary number. So first thing we do, we break it into 4 groups and we start from the least significant bit. So we count 4, draw a line, and then we have 1, 1, 0, 0, 1, and then 4 again, which is 0, 1, 1, 1, and then 4 again, which is again 0, 1, 1, 1, 1, and then we are left with 1, 1. Now we have to add in 2 zeros just to make it into 4. And then we convert these numbers separately. So this is equal to the hexadecimal number C. This is equal to 7, 7, and 3. And then we just write 377C. And this is the hexadecimal number. So we take each by 4 and then convert them here. Also very important, should there be fractions, let's say we have a comma and then binary, we just group them again by 4, adding zeros this way if it's a fractional number. So same thing for hexa to binary, so let's convert that number again. We got 377C. So we once again split them up and then write down in terms of 4 bits the nibble what number they are. So C is 1100, 7, 7, and 3. And then we just stick them together. And this is exactly the same number we got previously. So pretty easy, but you still have to practice a lot just to get the concepts down and not to get confused between binary, hexa, and octal, because the conversion methods are pretty much the same. You just have to remember to use 2 in binary, 8 octal, and 16 for hexa. Okay, and that's the end of the slide. If you have any questions, don't hesitate to email me, and good luck.